Good afternoon, dear viewers. My name is Simhan. Today, we will continue our course on interpreting the results of geochemical studies of oil, gas, rock, and formation water. Today, we have the 10th part of the seminar. Today's topic is practical interpretation of the results of Rock-Eval pyrolysis in different modes. This topic is important not only for geochemists, but also for anyone who wants to learn more about the source rock in which hydrocarbons are generated. If you want to interpret the results of Rock-Eval yourself, I strongly recommend watching this video till the end. This slide provides brief information about myself. I already talked about myself last time. Over the last 10 years, we have conducted geochemical studies on about 7,000 oil samples derived from 160 fields in Kazakhstan and Russia, within the framework of about 100 projects. Also, during this time, we carried out Rock-Eval pyrolysis on about 2,000 samples from about 50 fields in Kazakhstan, and our database has accumulated a significant amount of geological information in sedimentary basins. Here is information about the structure of our course, which consists of 14 parts. Of these, we have already showed parts related to oil and gas analysis. There are different types of techniques to study and characterize source rocks. In this seminar, we will consider only 5 main types. Last time I showed you material analysis and vitrine reflectance. Regarding formation water, I will show you the interpretation of results of ion chromatography and the elemental composition of water. In the last lesson, I showed you application of the results of material analysis, which are used to determine kerogen type, environmental condition of organic matter, and the type of hydrocarbons. Measurements of vitrinite reflectance in coal samples are also shown to assess the thermal maturity of the source rocks. Today I will show you an even more interesting part of Rock-Eval. This slide presents the importance of source rock analysis in evaluating exploration activities. For example, biomarker analysis is carried out not only for oil, but also for extracts derived from oil-saturated core intervals. For example, as can be seen here, we found hydrocarbon source rocks and extracts hydrocarbons from, as can be seen here, we found hydrocarbon source rocks and extracted hydrocarbons from them for carrying out gas chromatography and biomarker analysis. Then we compared the results with those of similar oil studies to discern genetic link between them. Results of Rock-Eval pyrolysis and vitrinite reflectance measurements are used for 1D basin modeling, based on which one can determine hydrocarbon generation time, generation temperature, and the volume of hydrocarbons generated or expelled from the source rock. The vitrinite reflectance results are used to calibrate the model. For example, on the right side of the slide, there is a plot of vitrinite reflectance versus the depth. Here, the true vitrinite reflectance values, which are represented by the circles, must match with the curved line for the model to be correct. There are many types of pyrolysis techniques and methods for evaluating source rocks. On this slide, I compare the advantages and the disadvantages of 6 different methods. For me, Rock-Eval is the most versatile and effective method because the analysis is fast and only small sample volume is required. You can easily find this tool on the market, and the cost of this analysis only up to $100. Of course, there are disadvantages as well. For example, if bicarbonates or siderite are present in the mineral phase, then erroneous results may be obtained for all parameters except S1, S2, and Tmax, because these mineral phases release CO2 at different temperatures. HOC stands for hydrocarbon analyzer with kinetics. That is a hydrocarbon analyzer with kinetics. Here, the obtained results are indicated differently. For example, oil 1 for the light fraction, oil 2, oil 3 for middle fraction, and K1 for the heavy fraction or kerogen. SourceRock analyzer is a prototype tool that is being used at Reservoir laboratories. Other pyrolysis, such as Fisher assay, pyrolysis, and in situ simulator, are mainly used in a single academic universities in the world. There are no such devices on the market yet. It is logical, given that the analysis take about a week and require painstaking work and a very large sample. Transformation of sedimentary organic matter under the influence of temperature and pressure give rise to the generation of hydrocarbons, and thermal cracking of kerogen, which in turn releases hydrocarbons. The operating principle of the pyrolysis is to create paleothermal condition for the hydrocarbons generation. The Rock-Eval method is based on the thermal modeling of the evolution of the source rock. This pyrolysis analysis on Rock-Eval is carried out in 4 modes. Bulk rock or basic method is used to characterize the source rocks. It enables to define the full set of available Rock-Eval parameters. Hopkin regime is used to obtain kinetic parameters on rocks and kerogens. Reservoir rock is used to identify the characteristics of reservoir rocks, sandstones, limestones. Organic matter mode is used for testing decarbonized coals and kerogens. This method is intended for the analysis of decarbonated major coals, as it allows the determination of higher Tmax. Here on the left side of this slide is the change in the Rock-Eval pyrogram from the immature stage to the over-mature stage, with maturity S1 peak, which is marked in green, and the S2 peak, which is marked in orange, decrease, while a shift in S2 to the right is observed with thermal maturity increase. On the right side of the slide, there is a table showing the obtained parameters, formulas, and their names. In order to take samples for source rock analysis in Rock-Eval bulk rock mode, we usually look at first logging data and then lithological description of the core. For this analysis, typically shaly rocks, mudstones, and coaly samples are selected for Rock-Eval analysis. Gamma ray logging measures the strength of natural radioactivity present in the formation. High gamma ray values in the log indicate the presence of shaly intervals, which we need for this analysis. In addition to clays, palomictic sandstones have significant radioactivity with minor clay content due to potassium-containing minerals such as feldspar, glauconite, and microcline. Therefore, in order to confirm the obtained intervals, we also look at the lithological description of the core of this interval. Sometimes we are brought cuttings instead of core. Then we look at the sludge logs where shaly intervals are given in green. We also pay attention to the XRD results to understand which minerals predominate in the sample. For example, this sample here is dominated by kaolinite, which is marked in yellow. Presented here are representative samples from each field that was done at for this Rock-Eval pyrolysis, as can be seen. The core samples were collected from different intervals spanning stratigraphic ranges from Paleozoic to Jurassic, and with different lithologies, carbonates, shales, coals. The results of pyrolysis of Rock-Eval cannot be immediately interpreted. Firstly, you need to make sure that the analysis is correct and the results is reliable. Firstly, if the studied samples have such low TOC and S2 values, even before and after the extraction, then there is no further interpretations needed for them. We can easily reject them as they are marked in yellow here. Secondly, if the Rock-Eval pyrogram shows bimodal distribution of S2 peak, then usually such distribution is associated with the presence of heavy hydrocarbons, resins, and asphaltenes in the rock. Because of them, the maximum value of S2 peak and Tmax shift towards lower temperature, which leads to incorrect interpretation. Such a pyrogram should not be interpreted as a source rock. Results in bulk rock mode are used to determine 4 source rock parameters. The first one is generative potential, or the amount of organic matter, which is determined mainly by the value of total organic carbon. The second parameter is kerogen type, which depends on the quality of the organic matter, which is hydrogen content. The quality of the organic matter determines whether the kerogen is oil-prone, type 2, type 1, or gas-prone, type 3. The third parameter is thermal maturity. This parameter indicates whether the source rock reached oil window to generate hydrocarbons or not. Using the fourth parameter, you can determine whether the identified hydrocarbons are indigenous or migrated. Here, indigenous means it was generated there. Generative potential. The amount of organic matter in the generative potential. The amount of organic matter in the rock is determined by total organic carbon. For shale, TOC values higher than 2 are considered acceptable, and values higher than 4 are considered excellent for hydrocarbon generation. Here is an example of the South Mangashlak Basin. Some Jurassic samples from Asar Karamanduan Chitawai northern Akkar fields and the Paleozoic Moimasha sample have excellent generation potentials. If reaching enough maturity, these layers could potentially be predominantly source rocks. The relatively high TOC values for Asar samples could be explained by the fact that they have higher values of residual carbon. Most of the samples from Pridorozhny and Chitubay fields demonstrate very poor potential, although the remaining samples are in the zone of average to good generation potential. There are other parameters that can be used to assess the generative potential of hydrocarbon source rock. These include S1 plus S2, because S1 value represents the proportion of the original genetic potential that was effectively transformed into the hydrocarbons, and the S2 value characterizes the residual oil source rock potentials that would have been used during the generation of hydrocarbons. Therefore, the sum of these parameters represents the generation potential. Type of kerogen. Determining the type of kerogen is important to identify the types of generated from rock hydrocarbons. In particular, type 1 and type 2 kerogens usually have initial superpellic organic matter of lacustrine and marine source and mainly produce liquid hydrocarbons. Kerogen type 3 usually formed from chemical organic matter, that is woody, plant, or terrestrial material, and generates predominantly gas. Kerogen type 4 usually consists of inert materials and doesn't have oil generating potential. Here is a Van Kravlen plot or diagram to determine the kerogen type of samples. According to this plot, the shallow Jurassic samples of Akkar are close to the zone of type 1 kerogen, and the data for other pre-Derogenic wells correspond to kerogen type 3. There are mainly 5 plots that can be used to determine the kerogen type. We have already shown the first plot. A plot of reactive carbon index versus Tmax is also used to determine the type of hydrocarbons generated. As can be seen in the plot, most samples can be oil-prone as long as they reach thermal maturity. It is always necessary to compare the results of different analyses to check the correctness and verify the conclusions obtained. For example, according to the results of Rock-Eval, 3 samples are shown to be oil-prone, which is also consistent with the results of mass-well analysis. Thermal maturity. To determine the thermal maturity of samples, a plot of Tmax against production index is used. According to this plot, several samples are in non-indigenous or contaminated hydrocarbons zone. The maximum Tmax values are observed in oil samples derived from the deepest pay zones of oil machine at. Interestingly, some samples derived from Jurassic horizon, for example, Jitterbug, reached the oil window, although its more submerged parts are still immature. Here on the left side, there is a real example of the generation of hydrocarbons from kerogen in Rock-Eval. As you can see, as temperature increases, hydrocarbons are being generated inside the rock sample. It is clearly visible that they migrate through the pore spaces. In the Tmax versus depth diagram, 3 stages are shown based on Tmax values: immature, mature, and overmature. Samples in the green region can be said to reach oil window and are considered thermally mature source rocks, which is capable of generating hydrocarbons. Based on the results, we can draw a conclusion that some ASAR core samples are active petroleum reservoirs that are capable of generating hydrocarbons, but samples in the lower pre-Derogenic are overmature. As I already said, it is always necessary to compare the results of different analyses to verify the correctness of the conclusion. We usually use vitrinite reflectance versus Tmax correlation diagram. As you can see, both samples are immature in this diagram. If possible, spot color index should be performed as well to compare with the first diagram. If S1 is high and the TOC value is low, it means that hydrocarbons migrated from other places and were not generated there. The plot shows that hydrocarbons didn't migrate from other places, but they were generated inside the rock sample. Now we do a practical task. Pyrograms and the results of Rock-Eval pyrolysis for Devonian deposits of field R are presented. Using the data, characterize the source rocks, determine thermal maturity, generative potential, kerogen type, explain the pyrograms as well. Here are the results of the practical task, so you can compare them. In the reservoir mode of Rock-Eval pyrolysis, we can calculate, determine asphaltene content of reservoir rocks and mineral carbon content as well. Anyway, this is still theoretical approach. which should be developed further, although there are many publications on it. In Organ regime, we can get kinetic parameters of source rock that can be used to calculate the amounts of and the time of hydrocarbon generation in a sedimentary basin. The most important information obtained during kinetic studies is the value of Arrhenius constant and the distribution of activation energy. This is a huge topic and we cannot cover it fully in this lesson. If you are more interested in our publications about kinetics, scan the QR and read the publication, our published papers. The results of source rock analysis can be used for 1D basin modeling, as you can see here. So if we have all data, we can calculate theoretical volume of hydrocarbons expelled from the source rock ourselves, and this consists of 3 subsequent steps. The table below presents the results of Rock-Eval pyrolysis of potential source rock A as well as its rough square from seismic data and the height from logging data. So here we can calculate, and using this formula, we calculated that 40% of generation process was completed in this source rock A. In the second step, we can calculate original TOC using the formula and F, and we have F value from the first step. In the third step, we can calculate theoretical volume of hydrocarbons expelled from the source rock using the TOC original value from the second step. Thank you for your attention.